Hey everybody, in this video I will do fine-tuning of Pi 1.5 model that was released by Microsoft only few days back. It's one of the very strong model given its size. So if you go to files and version in Hugging Face, you will see the size of the model is only 2.84 GB of PyTorch model file. So it is one of those that can be very easily be fine-tuned in a home-based GPU or even I think in Google Colab free version. But I have not tried with the free version of Google Colab. This is only tried with my 12 GB GPU in my local machine. So let's quickly go through the model, some of the basics here. The language model Phi 1.5 is a transformer based model with 1.3 billion parameters. It was trained using the same data source as Phi 1, augmented with a new data source that consists of various NLP synthetic text. When assessed against benchmarks testing common sense, language understanding, and logical reasoning, Phi 1.5 demonstrates a nearly state-of-the-art performance among models with less than 10 billion parameters. So that's the specialty of this model. It's a very small model, but the result from this model you will get is almost close to 10 billion parameters model. And further, we did not fine-tune Phi 1.5 either for instruction following or through reinforcement learning from human feedback. The intention behind crafting this open source model is to provide the research community with a non-restricted small model to explore vital safety challenges such as reducing toxicity, understanding societal biases, enhanced controllability, and more. For a safer model release, we exclude generic web crawl data sources such as common crawl from training. And about the intended use of the model, given the nature of the training data, Phi 1.5 is best suited for prompts using the QA format, the chat format, and the code format. Note that Phi 1.5, being a base model, often produces irrelevant text following the main answer. In the following example, so this point is crucial. During my fine-tuning, I also found that after giving me the correct answer that I was asking, it also produced some irrelevant text. So you have to be aware of that and you have to know how to control for that, but I will come to that in a while my fine-tuning is done. So let's go to my VS Code. Alright, back in my VS Code, and the first line is just installing all the required libraries, pretty common ones: Accelerate, Transformer, iNobs, Dataset, PEFT, Bits and Bytes, and datasets. Oh, I think I put datasets twice, so just... And this upgrade flag is for upgrading the current version. So I have commented out these two lines here. That's for if you are planning to push the model to Hugging Face Hub, then you should get your API and log into your Hugging Face CLI from here. But I'm not pushing this model to Hugging Face for now, so I'm just commenting out here. And then So in this line, tokenizer is the tokenizer from this model. So all standard line auto tokenizer from pre-trained, and you pass the model name, and trust remote code is obviously true here. So tokenizer.pat token, I'm making it equal to tokenizer.eos token. So basically I'm just selecting a token to use as pat token. And then I have to, because it's a fine-tuning based on quantized model, so I have to quantize it using the bits and bytes config. So again, 4 very standard and boilerplate line. Let's quickly go through these individual parameters here of the bits and bytes config. So the first one, load in 4-bit. This parameter is for loading the model in 4 bits precision. This means that the weights and activations of the model are represented using 4 bits instead of the usual 32 bits. This can significantly reduce the memory footprint of the model. 4-bit precision models can use up to 16x less memory than full precision models and can be up to 2x faster than full precision models. However, if you need the highest possible accuracy, then you may want to use the full precision models. And the next one is BNB 4-bit use double quant equal to true. This parameter enables double quantization, or also called nested quantization, which applies a second quantization after the initial one. It saves an additional 0.4 bits per parameter. And then the next one is BNB 4-bit quantype equal to NF4. This parameter specifies a type of 4-bit quantization to be used. In this case, NF4 refers to normalized float 4, which is the default quantization type. And the last one, BNB 4-bit compute D type equal to torch.float16. So this parameter determines the compute data type used during the computation. It specifies the use of the bfloat16 data type for faster training. The compute type can be chosen from options like float16, bfloat16, float32, etc. This configuration is needed because while 4-bit bits and bytes stores weights in 4 bits, the computation still happens in 16 or 32-bit. And here, any combination can be chosen by the user, that is by the developer. And the options are float16, bfloat16 and float32. And here I've chosen float16. And the matrix multiplication and training will be much faster if one uses a 16-bit compute D type. And the basic question you may ask is, does floating point 4-bit precision quantization needs any special hardware, or has it any hardware requirement? Note that this method is only compatible with GPUs, hence it is not possible to quantize models in 4-bit on a CPU. That's the only requirement. And among the GPUs, there should not be any hardware requirements about this method. Therefore, any GPU could be used to run 4-bit quantization as long as you have CUDA version equal to 11.2 or more installed. And keep also in mind that the computation is not done in 4-bit. The weights and activations are compressed to that format, and the computation is still kept in the desired or native D type. And after this, I'm just printing the entire model that will show me the entire model architecture with all the layers and the names of them, and we need that information. Why, that we'll see in a second. So when you print this entire model, you will get this full model architecture printed. So we can see that it's a PEFT model for causal LM. Then I have the base model, LoRa model. These are all coming from those LoRa classes. And let's see, this is WQKV. This is one layer which is linear 4-bit, and we need this name. Another name we need for this is, and within that you can see in features, out features, LoRa A, LoRa B, LoRa embedding A, LoRa embedding B, all these things. And another layer we need is out projects. We will see in a second that why we need this WQKV and out projects. And we need that because in the next step, I am going to define my LoRa config for my LoRa adapters. And one of the most important parameter here is these target modules, which I have selected, as you can see, WQKV and output project, out project. And these two names I got from these two layers. Here we can see WQKV and out projects. And remember, these names of these layers can vary according to the model architecture. So whenever you are fine-tuning with any other model, you have to print it out and check out for yourself what is the layer that you want to include in your target modules. Now, the question that will most commonly asked is, for LoRa, why we need to identify the target layers while fine-tuning. And to understand why we need to identify those target layers, we need to first have a quick overview of the mechanism of the low-rank adapters. So a neural network contains many dense layers which perform matrix multiplication. The weight matrices in these layers typically have full rank, meaning that a matrix does not have any linearly dependent or redundant rows or columns. In contrast to full rank, low rank means that the matrix has redundant rows or columns. However, when adapting to a specific task, the authors of the LoRa paper shows that the pre-trained language models have a low intrinsic dimension. A low intrinsic dimension means that the data can be effectively represented or approximated by a lower dimensional space while retaining most of its essential information or structure. In other words, this means that we can decompose the new weight matrix for the adapted task into lower dimensional matrices without losing too much important information. So the LoRa paper authors hypothesize that the updates to the weights also have a low intrinsic rank during adaptation. This means that they can be decomposed into the product of two smaller matrices, which significantly reduces the number of parameters required to represent the original matrix. LoRa focuses on approximating these weight matrices by their low-rank counterparts, thus reducing the model size and computational cost. Now, LoRa adopts the rank of the low-rank approximation on a per-layer basis. This is based on the observation that the different layers in a transformer may have different optimal ranks. By choosing the rank for each layer individually, LoRa allows for a more efficient trade-off between model size, computational cost, and performance. And the intuition behind these choosing the optimal layer is that different layers in a transformer model may have different optimal ranks for the. So first, the target layers for applying LoRa are identified. These are usually the layers that contribute the most to the model size and computational cost, such as the query and value projection matrices in the multi-head self-attention mechanism. This is due to the matrix multiplication operations required for their computation and the subsequent operation in the attention mechanism. And for each target layer, a low-rank approximation is computed with methods such as singular value decomposition or SVD or other matrix factorization technique. The objective is to find two smaller matrices whose product closely approximates the original weight matrix in the target layer. Alright, with that, we are almost ready to bring in our model, and that's what I'm doing here, defining the model. And I'm also telling the configuration of the model, actually the name of the model, and device map equal to, that would be a dictionary. And here I'm just telling which device the model should be mapped at. And because I have my one single GPU, hence I'm putting it at 0 here. And trust remote code equal to true, and quantization config is BNB config, which we have defined here. So let's quickly go through the various parameters of LoRa config. I have already discussed in detail this one, target modules, as to why I need that, etc. Now, the next one, hyperparameter, is R. So R represents the rank of the low rank matrices learned during the fine-tuning process. As this value is increased, the number of parameters needed to be updated during the low rank adaptation also increases. So intuitively, a lower R value may lead to a quicker, less computationally intensive training process, but may affect the quality of the model thus produced. However, increasing R beyond a certain value may not yield any discernible increase in the quality of the model output. And the next one is LoRa alpha. So this parameter is used for scaling. So according to the LoRa research paper, the original one, the updated weight delta W is scaled by alpha divided by R, where alpha is a constant. When optimizing with Adam, tuning alpha is roughly the same as tuning the learning rate if the initialization was scaled appropriately. The reason is that the number of parameters increases linearly with R, and as you increase the R value, the values of the entries in delta W, that is weight updates, also scale linearly with R. And we want delta W to scale consistently with the pre-trained weights no matter what the R value is used. That's why the author set these alpha parameter to the first R and do not tune it. The default of alpha value is 8, and then I have these dropout rate. So this is the probability that each neuron's output is set to 0 during training, used to prevent overfitting. So dropout is a general technique in deep learning to reduce overfitting by randomly selecting neurons to ignore with a dropout probability during the training. The contribution of those selected neurons to the activation of downstream neurons is temporarily removed on the forward pass, and any weight update are not applied to the neurons on the backward pass. The default value of LoRa dropout is 0. And then I have this bias parameter, which can take any of the values between none, all, and LoRa only. If all or LoRa only is used, the corresponding biases will be updated during the training, and the default value is none. And lastly, I have this task type. So this is generally just represent the type of task that the model is being fine-tuned for. That is all. So possible task type include causal LM, feature extraction, a question answer, sequence to sequence LM, sequence classification, and token classification. And after defining the LoRa config, I am doing a very important stuff here in this line, which is invoking get PEFT model that I have imported at the very top from the PEFT library. And PEFT stands for parameter efficient fine tuning, which is really have become one of the most important innovation in the recent time in the LLM space. So under PEFT approaches, it only fine tune a small number of model parameters while freezing most parameters of the pre-trained LLMs, thereby greatly decreasing the computational and storage cost. This also overcomes the issues of catastrophic forgetting, a behavior observed during the full fine-tuning of LLMs. PEFT has also shown to be better than fine-tuning in the low data regimes and generalize better to out-of-domain scenarios. So in almost all practical fine-tuning nowadays, people are using this method quite a bit. Now this method get PEFT model has one little issue, and that is it's really slow to execute. And the reason for that is PEFT does an unnecessary timing initialization, and so time is spent on weights initialization by torch.nn.init.timing uniform. Of course, the code developers of the PEFT library are working on this, and probably within a couple of days or weeks this issue will be resolved. But for now, to make the PEFT execution faster, that is the method get PEFT model, I am using this little extra code here, that is the entire cell what you see here. And this code is primarily for modifying the initialization routine for the two PEFT module, linear 8-bit and linear 4-bit, these two. So this modification script code first patches the init module so that the timing uniform does nothing at all. So here I am using this Noop method, and then with the context manager, I will come to that point in a second. You just need to paste this entire method or entire script before you call your get PEFT model. That's how it is supposed to work. And what I'm doing here is a way to alter behavior in a localized manner without making permanent or global changes to class definition or the corresponding libraries that I'm using. So if you are interested, you can just go in the details of this code. But for now, the key point of this entire script is that the context manager, this context manager here. So this method no timing is defined to temporarily replace init.timing uniform, that is this line, with a Noop method. And what is a Noop method? That's defined here, which actually does nothing. So by replacing this init.timing uniform with the Noop method, this timing uniform initialization is effectively disabled during the execution of blocks under this context, and that's the magic of context manager. So I'm defining these two new methods for new 4init and new 8init. These two methods are defined for linear 4-bit and linear 8-bit classes respectively. And in these methods, the no timing context manager right here, what you see right here and here. So this context manager is used here to disable timing initialization, and then the original initialization method is called with whatever arguments were passed. This way, the behavior of the initialization is modified without permanently altering the original methods of the PEFT library. So this is an example of a method overriding in Python. So as you can see in the last two lines right here, a linear 8-bit dot underscore underscore init equal to my newly defined this new 8-bit. So what this does is that the original init method of linear 8-bit and linear 4-bit are overridden with new 8init and new 4init respectively. This effectively replaces the initialization method of these classes with the newly defined methods that disables timing initialization. So basically everything remains just the same, but only difference is the timing initialization is not happening with my newly overridden methods. And once I disable that timing initialization, which was the source of the slowness of the getPEFT model method, then I call the getPEFT model method and then it will run much faster. That's the whole purpose of this entire script. Alright, now proceeding with our main fine-tuning notebook. So the next step before I start the fine-tuning is to tokenize my dataset and also get my dataset. So in this cell, it's just a standard code of loading the dataset. Here I'm using a very popular text dataset from Hugging Face, and then I'm using this util method tokenize to tokenize that dataset. So in the tokenize method, the padding true right here specifies that the sequence should be padded to the same length. Truncation true specifies that sequences should be truncated to a maximum length, and max length I'm keeping it at 512. And here in this line, actually this entire line, what is happening is the tokenizer's object call method is being executed here. The call method in Python is a special method that allows an instance of a class to be called like a function, and in the context of Hugging Face transformer library, the call method is defined within the pre-trained tokenizer base class, which auto tokenizer is part of. And if you go up, you will see that we are using auto tokenizer here to tokenize our input data. So the call method in the tokenizer object is designed to handle tokenization with a simple and easy to use interface. It takes the text to be tokenized along with other optional arguments like padding, truncation, max length, etc. to control the behavior of the tokenization process. And that's exactly what is happening here. In essence, the call method encapsulates the tokenization logic, providing a convenient and accessible way to tokenize text data while abstracting away the underlying complexity. And then this line, this simple pandas data frame kind of operation here, it's just a little pre-processing to make the formatting of my input data, which is made text, in a proper fashion. So the apply method right here is used to apply a function along the row axis of the data frame. That is, x is equal to 1 refers to applying the function row wise, which is what I'm using here, x is equal to 1. And also I am applying this lambda function. So the lambda function is passed to the apply method, which takes a single argument x. This argument x represents a single row of the data frame subset, which contains the columns prompt and completion. So if you go to made text, let me just go there and show you. Alright, this is the dataset that I'm using in Hugging Face, made text, and we can see that there's just two columns. One is prompt and one is completion. So basically the prompt column is just a question or prompt, and completion is the entire answer. That's the whole dataset, and there are 1.4 thousand rows, and it's pretty small dataset, so you can complete the fine-tuning very fast. So here the lambda function constructs a new string for each row that has the format prompt followed by the value of the prompt column, and then completion followed by the value of the completion column. The result of this apply method call is a series of strings which is then assigned to a new column text in the data frame, this text column. So this operation essentially formats the text data from the prompt and completion columns into a new column text in a specific way, which is later used for tokenization and training. And this new format in the text column allows the model to understand the context between prompt and completion during the training phase. All right, and then I am making use of from pandas method to create my data. So you can see the flow of the data here. That is, I first got my data using load dataset, then converted it to pandas using toPandas method, because I had to do these pre-processing formatting changes here. And after that, when my dataset currently after this line is a pandas data frame, and then again I am using dataset.fromPandas and passing it the previous data df to get my this variable data, which is required for Hugging Face training. And once my data is fully ready, then I am ready to tokenize it. And the next line is doing just that. It is using the map method and the tokenize method that we have defined earlier to apply the tokenization for each row or for the entire data frame actually, or entire data set here. And this tokenized data is what I will be using in the next step during the actual training. So here I am defining my training arguments and I have these commented out code here. Actually, it's just exactly the same parameters, that is both are defining my training arguments. Only difference is this line, push to hub. So if you want to push to Hugging Face hub, then you should make it to true. But because right now I'm not pushing it, so this is my training arguments actually for this particular run. So here you can see these are all very obvious: per device train batch size, gradient accumulation steps, learning rate, LR scheduler type, cosine, save strategy, epoch, logging step 100. Yeah, these are pretty usual. Okay, max steps, sorry, that should be 1000. And for now, I'm running just one epoch. And once you have defined your training arguments, then the next obvious step is just run the trainer class. Trainer class is one of the most used and most popular class in the entire Hugging Face library. So you pass the model. Your train dataset is my tokenized dataset that we just tokenized in the previous step right here. And then args, training args, data collator is data collator for language modeling class. To that, it takes a tokenizer and MLM false. And then just do trainer.train. And again, if you want to push it to Hugging Face hub, you have to run this line. But for now, I have kept it commented out. And when training, you will see this particular warning coming for each of those steps, which reads attention mask is not supported during training. Using it might lead to unexpected results. Now, the problem here is that Phi 1.5 was pre-trained without padding, and the implementation of Max Former Sequential for Causal LM released by Microsoft with the model does not support attention masking during training. In this model, pad tokens are interpreted as normal tokens. You would have to modify that mix former sequential for causal LLM to add support for the attention mask. But not to worry, because Hugging Face core developers are working on this. So they have already sent a pull request to integrate with Hugging Face transformer library. So in very soon, attention mask will be indeed supported. For now, having this warning will not really affect your result. You can just ignore it for now. Okay, so after the training is complete, you need to save the model. So you just do model.save pre-trained and give it a name. And then you have to reload the base model. So in the next cell, that's what I'm doing, reloading my base model, which is original Microsoft Phi 1.5. And then I have to also load the PEFT model, that is PEFT model.from pre-trained, and that's my model, and give it a name. So this line right here, PEFT model.from pre-trained, actually instantiates a PEFT model from a pre-trained model and loaded PEFT weights. And so once you have your PEFT model, then finally you have to invoke this method, merge and upload, which merges the LoRa weights back into the main model. So you get back a base model with the LoRa weights applied. And finally, you just need to save it. This is my final fully fine-tuned model. And here, of course, I'm saving it in the local machine. So I'm just passing a string as the name of the model to be saved. But if you are pushing it to Hugging Face, you have to do model.push-to-hub. So overall, the total flow, the workflow that happened here right from the beginning is this. Load the base model, train the base model, save the LoRa adapter, reload the base model at full precision, then merge the LoRa weights with the base model, and finally just save it. And now the absolutely final step, which is inferencing on my pre-trained model. So here I am just doing the regular steps. First, loading my pre-trained model. So this is no more the original base model. This is the fully fine-tuned pre-trained model that has been merged with the LoRa weights. And then tokenizer remains the same. That is a tokenizer for this particular model, which is coming from the original base model. And now for the inputs, I am passing tokenizer to the tokenizer this particular prompt. I'm having headache with headache, but no fever. What could be the cause? Return tensor PT, return attention mask false. So that will produce these inputs, and then I have to generate, I have to apply the model.generate on those inputs and max length 512 and get my text, the actual text, by decoding the outputs with the first element of the outputs. And finally print these decoded text, and that's what I got. Special tokens have been added, the vocabulary, make sure the associated word embeddings are, okay, these are just not necessary here. So I am having headache with, so this is my prompt and this is the answer. The cause of your headache could be stress, lack of sleep, or dehydration. Yeah, quite simple and quite right. Now, one particular thing to note here that with this Pi 1.5 model, if you don't fine tune the model fully, it will continue generating until the maximum length has been reached, that is 2048. That is, after this answer, you will get a lot of extra text, which will be mostly irrelevant. But that's in the case when you do not fine-tune the model to the fullest extent. Alright, so that's pretty much it for this video. Stay tuned because I am going to do a whole range of fine-tuning videos over the coming weeks and days. So see you in the next one. Thank you very much for watching.